You may have been taught or yourself found an occasionally useful form of reasoning. You start with known facts or axioms about how the world works, and then, only using those axioms, arrange them in such a way that you build out new ideas or theorems. Since theorems are derived from axioms, they can also be accepted to be true and used to build out more theorems. For example, we could state 3 axioms. 1. An apple exists. 2. Every apple has a core. 3. If an object exists and contains another object, both objects exist. Technically, we never said an apple core exists, but you can show this from the axioms. 1. An apple exists by axiom 1. 2. Since every apple has a core by axiom 2, a core exists by axiom 3. Your brain might be able to process these facts very quickly. A piece of paper or a computer cannot. But if you look at your train of thought from the right angle, you might find a very elegant way to explain it on paper. In this process, you have also proven that your intuition is correct, because under your system, the paper agrees with you. This ability to create common sense in a programmatic way is very important to the field of artificial intelligence. Let's briefly introduce 2 related concepts before getting to the rest of the video: knowledge graphs and ontologies. Ontologies are similarly old to axiomatic systems, having roots deep in philosophy as theories of being and non-being, but have taken on a slightly narrower meaning in modern computer science. This definition for ontologies from Geeks for Geeks is pretty biased towards programmers, but might sound familiar. Ontologies are networks consisting of the following core objects. Classes represent categories or groups of similar objects. Instances, specific examples of a class. Properties, characteristics or attributes of classes and instances. Relationships, how different classes or entities are connected. Constraints and rules. Constraints define conditions or restrictions within the ontology. Some of you might recognize the very object-oriented phrasing of this definition. If you step back a little and squint, however, classes, properties, relationships, constraints, and rules are all examples of axioms or theorems. In our earlier system, axiom 1 would be a class representing an apple with the property of existing. Axiom 2 would describe a class representing a core and a relationship between apples and cores of apples having or containing a core. Then axiom 3 would be a rule. If the network we just drew was a board in a board game, the rules of an ontology are instructions that might come with the board game. The main idea of 21st century ontology projects is that if you gave an ontology to a computer that could interpret it, it could find theorems automatically and add them to the database, then repeat the process, slowly building out an understanding of reality in the same way a human would, if they were locked in a cave and all they had to understand the world was a set of axioms. I can't say I recommend this as a parenting strategy, but it should work on paper. A good ontology could get you a robot super philosopher with a strong intuitive grasp on the fundamentals of physics, patterns, and even morals. From my outside understanding, knowledge graphs are similar to ontologies but less formal. There's a lot more debate on how knowledge graphs are defined, since it's really more of a corporate buzzword that Google used to refer to a centralized relational database in the early 2000s, and was then adopted by other corporate entities to refer to their own internal knowledge bases. Basically an internal corporate Wikipedia, with maybe more of a leaning towards bot crawling and rich searches than readability or public good. The relationships between objects in a knowledge graph are labeled, but there doesn't need to be strict rules on how links can be interpreted, like in an ontology. The trade-off between the two, then, is that knowledge graphs are harder to process automatically, but easier to build and maintain. For examples of knowledge graphs in the wild, I recommend checking out Wikidata. Today, we're going to apply some of these ideas. First, we're going to learn some math. I'm going to build a knowledge graph of some math subjects, then add rules to it and try to grow the knowledge base with them. The goal is to explore what it actually means to build one of these databases and reflect on how building one can be valuable. The next chapter will talk a little more about how I arrived at this project, as well as get more into the day-to-day of the actual construction of the knowledge graph. Then I'll demonstrate some basic ability of the knowledge graph to generate knowledge in a way that's similar to how an ontology works. This video used to be twice as long. I spent a lot of time on experiments with the structure of taking notes, effective definitions, artificial intelligence, and rich examples of the 3 subjects I intended to cover with my knowledge graph. What this led to was a lot of work for little results. I'll still tell some simple snapshots of the process here that I think are interesting, but these are just suggestions. In your own reality charting ambitions, you could probably ignore all of them and still be fine. If you're really just interested in the results of the knowledge graph, then you can skip ahead to the next chapter. But this chapter will include some helpful context that might leave you confused if you don't have it when we get into the applications. This project started when I took a class called Theory of Vector Spaces in my last semester of college. My note-taking was surprisingly effective. I used Obsidian, a software for taking notes, and organized concepts into classes of objects. A class document would have a plain text definition, followed by a list of examples, links to other documents describing instances of the class, and properties, links to other documents describing properties of the class. I didn't do this with the intention of building a knowledge graph or ontology. I did it with the intention of having a way to write information down that I could effectively study later while also keeping up with the lecture. But I had heard about knowledge graphs here and there, and when I looked more into it, I realized I was making something. It could be called a knowledge graph, since most of the links between documents were sort of labeled as property of or example of, by means of whether they appeared in the properties or examples section of the class documents. Most importantly to my motivation, I wanted to see if other math subjects would fit into the Obsidian project, and whether the resulting knowledge graph would be at all useful. The 3 examples I'm going to cover from this process are what it means to be abstract, what it means to be like Wikipedia, and what it means to be unique. 1. What it means to be abstract. The 3 subjects I ended up including were linear algebra, as taught through the class Theory of Vector Spaces, using the textbook Linear Algebra Done Right by Sheldon Axler; graph theory, reviewed from a class of the same name I took a few years ago, using the textbook Introduction to Graph Theory by Douglas West; and topology, self-taught from Algebraic Topology by Alan Hatcher. To temper your expectations, I struggled with the pacing of studying required for this video. Topology was very foreign to me, and I didn't even make it past the introductory 0th chapter, as we'll discuss later. And in graph theory, I neglected all the work my professor 2 years ago must have put into making the class possible in only 2 months. I tried to cover everything I came across in the book, and only had time to make it through the first 2 chapters. Despite all that, the effort did produce a useful result, and it was definitely enough work to run into a lot of the edge cases you might run into if you were trying to construct a more comprehensive knowledge base. There's also an important through line of these 3 subjects. They are all what I would consider to be abstract math. To understand what I mean by this, let's talk a little more about those ontology terms from earlier. Classes, for our purposes, are notes in the knowledge graph that define whole collections or categories of objects. Instances are specific objects that belong to a class. In my notes, I call this being an example of a class. The line between the 2 is fuzzier than you would think, since sets in particular can be treated like objects and collections. But let's just pretend there's a nice line between the 2 for a second. In high school, if you did what I did in college and took notes with as many separate documents as possible for your Algebra and Algebra 2 classes, You would probably get a bunch of examples of equations. You might have a few documents describing properties of equations or some general definitions, classes, but most of the notes would be examples, instances. However, if you did the same thing in graph theory, you would end up with mostly discussions of classes and their properties. Examples would be present to help build intuition, but they would ultimately take a back seat. Some of the problems in West's graph theory textbook do construct specific graphs via algorithms or diagrams, but most of them instead construct a class of graphs by stacking properties together. The expectation is that you're more thinking of the problem in front of you as a set of properties, which you can then combine with what you've learned from previous chapters to show that some other properties must also apply. The knowledge graph that I built is then more abstract than not abstract. It mostly deals in classes and properties. And knowledge graphs that hope to make sweeping statements are likely to be in a similar position. 2. What it means to be Wikipedia. I wrote these notes using the Obsidian editor. In Obsidian, you can type out text like normal, but if you then type out 2 open square brackets, followed by the name of another document in the vault or master folder for the project, a hidden database records that there is now a link between these 2 documents. The link then displays as the title of the document in purple text. For me, the main highlight is the satisfaction of going to the graph display mode and watching all of your documents represented by points with physics, and links drawn as lines between them, applying spring-like forces. There's a lot of small quality of life things in the editor too, but it's really not a super fancy project organizer. It's notably less complicated than MediaWiki, the system used by Wikipedia to run Wikipedia, among other things. Something both MediaWiki and Obsidian have in common are the in-text links. No matter how you name your documents, eventually you're going to need to place a link in a way that doesn't make complete grammatical sense. For example, if you wanted to define everything, and everything was defined once, there would only be one way to use any given term, and you would be navigating a language with no wiggle room for double meanings or shorthand. I was able to avoid most of these situations with a few simple tricks. Properties and examples I almost always linked in bullet-pointed lists, and labeled them using the numbers they were given in their respective textbooks. These lists keep the links outside of any paragraphs where they could cause grammatical conflicts. Even then, there are some links I wanted to reference in text, but couldn't fit in text in a nice way. A great example of things going wrong is with the document Eigenvalues and Eigenvectors. Eigenvalues and eigenvectors are paired objects. You really don't get one without the other. So for the sake of my intuition, I made an unconventional decision to create the document titled Eigenvalues and Eigenvectors as one word to link to. So when the Axler book made a statement like, suppose T in LV, then every list of eigenvectors of T corresponding to distinct eigenvalues of T is linearly independent. The statement I end up with is, all lists of distinct eigenvalues and eigenvectors are linearly independent vectors. Since the terms are merged together, my definition misses the subtlety that it's the eigenvalues that have to be distinct for the eigenvectors to be independent. The popular solution to any problem with in-text citations is not some mysterious tool. It's something called aliasing. In-text links are perfectly capable of referencing a document of one title while having separate text content. For example, eigenvalues and eigenvectors could be linked as just eigenvalues, or just eigenvectors, depending on how the document is being used in context. Both Obsidian and MediaWiki have fairly clean solutions for this. But then you have another issue, which is that you can't immediately tell, just from looking, what document a link is referencing. It also takes more work to type out aliases. I experimented with using them in my math classes, but it interrupted my workflow just enough that it was hard to keep up with the lectures. You have to think more about how links are used, and whether you're linking the correct document, and if links should even be made. Since aliases allow for looser usage of documents, that leads to more overlap between concepts. Wikipedia often demonstrates these problems by having documents include links that aren't closely related to what's being talked about in context. All this thinking was way too much of an obstacle for me when I was just taking notes, though including aliasing and therefore being more like wikis might be worthwhile for more careful projects. 3. What it means to be unique. Both Hatcher and Axler's books spend a decent amount of time on a concept called quotient spaces. Honestly, I was expecting a lot more issues like this. Both books have their own definitions for quotient spaces. However, this leads to aliasing, since the term quotient spaces could refer to one of two things. Really, I want one document that both subjects could link to when talking about quotient spaces. The process of turning multiple points of data into one is called deduplication. This is where I really started to believe in the potential for this project, since it felt like I was learning something from the graph in this process. Theory of vector spaces deals in vector spaces, and topology often deals with cell complexes. In theory of vector spaces, a subspace is a subset of vectors which cannot be escaped using the operations in that space. If you draw a straight line through 0, 0 in the xy plane, adding coordinates of any 2 points on the line will result in another point on the line. The same goes for scaling coordinates, making that line a subspace of the plane. Similarly, in topology, a subcomplex is a set of cells in a cell complex that cannot be escaped via the attaching maps connecting cells together. Quotient spaces of vector spaces are the sets of all translates, thought of as vectors, quote-unquote, added to subspaces. A translate of a subspace U by a vector V is written V plus capital U. If V is inside U, such as being on that line in the xy plane, V plus U is defined as being equal to 0 plus U, the 0, 0 point. The set of all translates of U, all choices for V plus U, is written capital V divided by U. Quotient spaces in topology are subcomplexes identified to a point. For a complex X, if you had a subcomplex capital A with cells A, B, C, and identified it to a new point P, to the same effect as saying A equals B equals C equals P under the quotient. This is denoted X divided by A, the quotient of A on X. The trick to merging these two definitions is to see the through line that both quotient space definitions involve identifying a subspace or subcomplex to a point. The way that quotient spaces are constructed in theory of vector spaces, which at first appears to be something entirely different from the vector space itself, and the way that they are constructed in topology through the collapsing of a subcomplex to a point, seem very different on the surface if you don't know how to rephrase the problem. Rotating the problem and seeing it that way was very helpful to my understanding of both subjects. But why go through all this work in the first place? Some systems avoid duplicate names like the plague, but MediaWiki's disambiguation feature, its ability to turn links that could point to multiple documents into lists of options, largely avoids the problem. However, mathematicians take a lot of inspiration from each other, so if two documents in your math notes are of the same name, it might be because they're related, and you might learn something from the process of trying to merge them together. AlphaProof is an automated math problem solver and proofwriter. It is a combination of a training technique used for a previous machine called AlphaZero, which was built by DeepMind to play chess and Go to amazing effect, a strategist. The second ingredient is an LLM, some version of Gemini, which formalizes problems into a language called Lean, a programming language capable of verifying proofs automatically. AlphaZero is trained to think in Lean. The LLM then translates problems into Lean for AlphaZero to solve. Then, the resulting Lean proofs can be checked for correctness automatically. I'm fascinated by this seemingly symbiotic relationship. A social LLM that understands language, a more introverted strategist that understands logic, and a machine that acts as the cruel reality of nature, telling the relatively unstable neural networks what they can and cannot do. The knowledge graph in this case is supplied by Lean. Lean knows about the math world and how it works, and indirectly provides them to the rest of the system through its yes or no answers on whether proofs are valid or not. Lean operates off of an axiomatic system, much like the ones we described in the introduction. In the following experiment, we're going to replace the social LLM with me, AlphaZero with me, and Lean with me. Then, we'll see if I can actually build proofs using the knowledge graph I built from the previous chapters as the math world. To do this, we first have to turn our knowledge graph into a loose ontology by adding rules for how to interpret relationships. As discussed earlier, we can roughly classify relationships in the knowledge graph into examples and properties. So, let's add some rules for how to use those relationships. 1. Examples of classes can inherit their properties. 2. If classes X are defined by properties P1 through Pn, and objects A have the same properties, A is an example of X. With that out of the way, let's test if our very loose ontology can actually generate some knowledge. For problems, I'm going to use exercises from the textbooks, one from each. I didn't include number theory or set theory in my notes, but they are very fundamental, so some facts not included in the knowledge graph will make an appearance. Hopefully this wiggle room doesn't offend you. 1. Subspace bubble. For vector spaces V with subspaces V1, V2, prove that the intersection of V1, V2 is a subspace of V. This is a good starting point since we've talked a good bit about subspaces already. Since subspaces are defined as being closed on addition in scalars, the trick here is to show that the intersection is also closed. But can I express this from my base lemmas? For all uv in the intersection of v1 and v2, and all scalars lambda, show that u plus v is in the intersection, and lambda u is also in the intersection. By our first lemma, since u and v are examples of vectors in the subspaces v1, they inherit the properties from subspace v1 of being closed on addition and scalars inside v1. For this reason, u plus v and lambda u will always be inside v1. By the same logic, uv inherit the same properties from the subspace v2. By definition, these are the spans of the intersection. Spans are another object defined in the knowledge graph as the set of all sums and scaled vectors from a certain set. Every member of the spans is in the intersection, as we just showed. By definition, then, the span of the intersection is the intersection itself. It follows from the definition of spans that the intersection is closed on addition and scalars. Since spans contain all sums and scalars of its vectors, no sum or scalar will escape it. Therefore, the intersection is a subspace itself. While this might seem painfully obvious to some people or completely unhelpful to others, I want to point out that the lemmas, the rules, are standing in for a part of my intuition. I chose what lemmas to apply and where, but I had to use them to make progress. If you wanted to, you could exhaustively search all notes in the knowledge graph and check whether they are applicable for each of the lemmas, and repeat until you reach a solution. Or you could set up some LLM-based solution to pick out notes which are likely to be helpful. I argue that my knowledge graph has just generated knowledge. The knowledge graph did not have this exact proof inside of its database, and yet contained enough information to show it was true when I paired it with certain existing information. In this case, I used the definitions for subspaces and spans, paired with the axioms I made up earlier. I did have to include something that wasn't actually inside the knowledge graph, the definition of an intersection of two sets, which is used implicitly to state that U and V are members of both V1 and V2. We'll see other small things pop up here and there, and it is actually important to recognize these missing elements, because it points to why knowledge graphs and ontologies have some trouble getting off the ground in a practical sense. 2. Euler. Let's try a problem in graph theory. I'm going to add a lemma for induction. For properties pk of classes xk, where k has a successor k plus 1. If p1 is a property of x1, where 1 is some starting k, and pk plus 1 is a property of xk plus 1, when pk is a property of xk, p is a property of x for all k. Now, let's get some quick definitions from the notes before moving forward. Graphs are sets of vertices and edges, where each edge relates two vertices together. They are typically drawn with the vertices as points and the edges as lines between vertices. Trails can be defined as alternating sequences of vertices and edges, where each vertex is related to the edge on either side of it in the sequence, and no edges repeat. Trails are considered closed if they start and end at the same vertex. A graph is Eulerian if a single closed trail can cover all of its edges. We've been working with an example of a non-Eulerian graph, though that might not be obvious at first. That's going to be at the root of our problem, so here's a copy of that graph that I added a couple edges to make it Eulerian, along with the closed trail that covers all of its edges. We'll talk more about how that was done after the proof. 2 more quick definitions. Don't worry, this is the most complex problem we'll do today. First, graph decompositions are separations of the edges of the graph into sets such that each edge appears exactly once in the sets. Think of it as breaking the graph into pieces. Second, cycles are closed paths, trails with no repeating vertices or edges, but which start and end at the same vertex. We're going to think of these as circles for simplicity. Those are all the lemmas and definitions from my knowledge graph that we'll need. I'll pull a couple extra notes for properties here and there, but those will only be from the classes I just introduced. We now have enough to prove that all Eulerian graphs which have closed trails that cover all their edges, decompose into circles. The notes say that Eulerian graphs have the property of all vertices being of even degree, property 1.2.26, meaning that every vertex touches an even number of edges. By definition of Eulerian graphs, as long as there are more than 0 edges, a closed trail exists that contains every edge exactly once. By property 1.2.5, a cycle then also must exist inside the trail. Therefore, we can create a decomposition of the graph into the cycle and the remainder of the graph. By definition of cycles, cycles have 2 edges on each vertex. So removing a cycle from a graph removes either 2 or 0 edges from each vertex. Therefore, since our graph was even degree to begin with, the remainder must also be even degree. By definition, even degree graphs are Eulerian as long as they have more than 0 edges. So, by induction, the graph decomposes into cycles plus a remainder. If the graph is not infinitely large, which it is usually assumed not to be in graph theory problems, a cycle can always be removed until all edges are eventually removed from each vertex. At this point, no cycle can be found because 0 edges remain in the remainder. We can see this process again for the example I constructed earlier by adding 2 edges to a non-Eulerian graph. Note that this proof is not enough to say that all graphs that decompose into cycles are necessarily Eulerian, also known as the reverse of a proof. But it is true. You can show that by using cycles to build a trail and showing the trail has no repeating edges and can be closed. Additionally, I want to point out how simple the visual is of showing the Eulerian graph is covered by a trail, then breaking the trail into cycles, one by one, versus how complicated the explanation is in graph theory language. Doing this proof just now really helped me understand why some of my professors were so strict with how I worded proofs. It's super annoying to write math this way, but what it essentially gives you is a strong argument. You don't have to rely on your intuition for example, graphs that are too big or dense in edges to draw on paper. 3. Bakery. Some donut places sell really airy donuts. I want you to accept for a moment the idea of a donut that's completely empty on the inside, basically a thin shell of crust with icing. Then, imagine taking a pencil and poking a hole into the donut. Just a tiny hole on one side, not all the way through, so that there is a tunnel from the air on the inside to the air on the outside. Now for something a little less physical. Imagine you could stretch the hole however you like, as long as the donut doesn't split into 2 pieces. The puzzle then is to produce 2 rings joined at a point, also called a figure 8 shape, just by stretching the hole inside the donut. More generally, the problem is to show that a donut with a hole poked in it is homotopic to a figure 8. Informally, this is easy to think of as there being a set of stretches that shrinks one shape into the other. The intuitive solution is to stretch the hole vertically, then stretch the hole horizontally. The result is 2 rings intersecting at a point. And so, we have proven the shapes are homotopic by showing a construction. To construct this proof rigorously, however, we're going to have to describe cell complexes. I briefly discussed them earlier, but we'll need a more precise definition now. Cell complexes are like an upgraded version of graphs. Instead of just vertices and edges, there are now 0 cells and 1 cells, which correspond to relations between 0 cells. More generally, cell complexes can contain n cells, which correspond to relations between cells of the next level down, n-1 cells. For example, 2 cells mark relations between 1 cells. The 0 cells are like points. They serve the same purpose as vertices. And the 1 cells are like edges, relating 2 vertices together. Cells in a cell complex have attaching maps describing exactly how they attach other cells in the layer beneath them. The attaching maps for 1 cells are usually pretty simple, but even 2 cells, and especially higher cells, can have very complicated instructions for how they relate the corresponding elements in the next layer down. There's a lot of subtlety I'm skipping over here, but it's not worth the time today. The example below will have a simplified description of an attaching map for a 2 cell, and that will be enough to build our proof. A torus, or donut, like in our problem, could be considered a 2-dimensional cell complex. Take 1 0 cell, or vertex, call it X. Attach 2 1 cells, A, B, so that both of each of their endpoints are in X. Note that this is already the figure 8 shape we want to build. Let's call this cell complex A. To complete the torus, we're going to add a 2 cell, Z. To represent the attaching map of Z, let's draw Z as a square sheet. The top and bottom edges will both label A, and the other edges B. Now imagine rolling up the sheet to connect A to A and B to B. The resulting shape is a donut with nothing inside, called a torus. This is the canonical cell complex of a torus, expanded from my notes. Now, what does poking a hole mean in our cell complex? Let's think of a simpler example, ripping an edge in a graph. If you rip an edge in a graph, you effectively remove the edge. Yes, if you are representing the graph using a physical network of string, then cut the string. There would still be bits of string hanging from the points where you cut. But the important fact is that the two endpoints of the edge are no longer related. The one cell, the edge, has effectively been deleted when you cut the string. We can make the same argument about breaking a two-cell. If we poke exactly one hole into a two-cell, the face can contract into its edges like a popped balloon. This isn't the case for all forms of attaching maps of two cells, but it is the case here. All this work is just to define what poking a hole in a donut even is. We don't need to invoke our knowledge graph yet, because we're still in the process of formalizing the problem. This is all work that could be done by our social LLM in alpha proof. After that, the problem sort of solves itself. Cell complexes define a shape's homotopy type. Two shapes with the same homotopy type are homotopic by definition. A torus constructed from A plus a face. Poking a hole removes the face, leaving behind A. Since complex A constructs a torus with a hole poked in it and a figure 8, the shapes are homotopic. 5 notes were used in this proof: the definition of cell complexes, the definitions the textbook had for a torus and figure 8, the property of cell complexes that they determine a shape's homotopy type, and the definition of a homotopy type at the end. One additional definition was formed, that poking a hole is equivalent to removing a two-cell. This proof demonstrates how problems can be skewed towards your formalization engine. The actual proof was only a few lines, but the act of creating all the necessary definitions, the complex A, the act of poking a hole, took up a lot more writing and editing on my end, and was by far the most difficult part of the proof. Obviously, I haven't made a practical tool here. As much as that would have been awesome, I want to emphasize that there's nothing special about the axioms that I used. I made them up. If you made an ontology with your own rules, you could probably still make use of it. In fact, many of you could probably come up with something better than what I used. I didn't spend that long doing it. The Lean documentation has some pretty good tips on how to actually do this, and some examples of starting axioms that it uses, too. If I wanted to make a practical tool more than anything, I should have done something similar to alpha proof. Pick a unifying theory, then use it to explain everything I was studying. A unifying theory is just the most straightforward way I can think of to formalize problems from or involving multiple domains. But that doesn't make this exercise useless. Aside from quotient spaces, there was a ton of little things from my math education that I felt I had filled out from analyzing them with new perspectives. If you're interested in studying math on your own, I can't recommend enough to build your own graph or wiki of your studies, just to see what insights it gives you. One problem that really fascinates me is the problem of quasi-polynomial graph isomorphism. It's a relatively recent discovery. The still evolving field deals a lot in group theory, which has a lot to do with topology and graph theory, but also exists fully within its own language, which I do not speak. Yes, I could have chosen group theory as a subject to add to my notes. Originally, I had the lofty goal of including all subjects I studied in college in my knowledge graph. I wanted to cover a lot more subjects in the video, and even benchmark my knowledge graph against other existing ones. This video is already a little unfocused and lengthy. It definitely did not need more of the thousands of words cut from the script during editing. My point is that I didn't get some magical understanding of higher math in general from this project, and I wasn't expecting to. My major in college was actually computer science, especially focused on software engineering. I always saw math as much as a means to an end for better software abstractions, as I did something interesting in its own right. This project has really strengthened my belief that network documentation is probably the strongest format that one person or a team can turn to when sculpting and better understanding a concept. One of my goals was to make a cool math database that shows the connections between various subjects, and I think I succeeded. When I run the visualization, some concepts from topology are almost nestled in between linear algebra and graph theory, very much gluing the concepts together visually. Through dimension, quotient spaces, cell complexes, I like to think of topology as the subject where space meets networks. I also want to point out that ontologies, a big word in AI right now, is more accessible and useful to you than you might think. I wouldn't say I have the best math problem-solving knowledge graph on the market. In fact, we just used it to show common pitfalls of the technology. But those are some of the same limitations faced by massive professional endeavors of the same nature. It would have taken much more time and pain for me to develop a specialized artificial intelligence model with the same capabilities as this project. The act of writing things down myself, as opposed to a more computational or formal process, was also valuable to my actual ability to learn what I was studying.